Introduction to Function Inverses. In this video, we'll determine the inverse of functions from a table of values, a graph, and an equation. Let's start with terminology. A relation is a set of ordered pairs. A function is a relation in which each element in the domain, or your input, is paired with exactly one element in the range, or the output. If R represents a relation, then the inverse relation is the set of ordered pairs obtained by reversing the coordinates in each ordered pair of R. For example, if A, B is in relation R, then B, A is in the inverse relation. The inverse of a relation may or may not be a function. If a relation and its inverse are both functions, they are inverse functions. So let's find the inverse of a function. We'll start with a table. And this one will be our relation we'll call R. We'll start with a set of input values, our domain, our x values, and their corresponding y values, the range. First, let's consider, is this relation a function? Is each input paired with exactly one output? Yep, R is not only a relation, it is a function. Now let's find its inverse. What we're going to do is we're going to switch. The range will be the new domain, and the former domain will be the new range. So here's our domain. It's the previous range values, and our new range will be the previous domain values. Is the inverse of R also a function? Is each input paired with exactly one output? Nope. I can see there is an input, namely 2, which has more than one output. Therefore, the inverse of R would fail the vertical line test. It is not a function. Since both R and its inverse are not functions, we cannot say they are inverse functions. Instead, we simply say these are inverses. So, not a difficult task to find the inverse of a function from a table. Let's move on to a graph. So we'll start with our coordinate plane, and we'll show you what this looks like. First, we'll start with a quadratic function, a parabola. This is the regular function. This passes the vertical line test. It is a function. And its inverse looks like this. Notice its inverse is not a function because it does not pass the vertical line test. And turns out they are functions because they are mirror images over the line y equals x. So that's what we're going to use to determine the inverse of a function from a graph. We'll graph the line y equals x and we'll find the mirror images. Let's get practice with that. So here, let's start with a function with a table of values. In fact, this is the previous relation that we looked at earlier. So we can graph these ordered pairs. Let's graph -1, 2, 1, 2, 2, 4, and 3, 5. And now let's graph the line y equals x. And what we're going to do is we're going to consider each point in the relation, and we'll draw a perpendicular toward the line y equals x, and then find the mirror image on the other side. And this is the inverse of the first point right here. And we'll look at the next ordered pair in our function. We'll draw that distance to the line y equals x and its mirror image on the other side, and there's our point, which is the inverse of 1, comma 2. Now let's find the inverse of 2, comma 4. And finally, the inverse of 3, comma 5. So now if we wanted to find our table of values in the inverse of R, we're just using those reflected points, and we're justifying using a graph what we had talked about earlier using a table. Okay, so inverse of a function from an equation, we're going to consider a linear function, y equals x plus 3. And instead of graphing this, what we're going to do is we're going to switch the x and the y. So we're going to rewrite the equation by just substituting x where I see a y and y wherever I see an x. Now I'm going to rewrite this equation so y plus 3 is on the left-hand side of the equal sign. And I want to solve for y by subtracting 3 from both sides. So the original function, y equals x plus 3, has an inverse, which can be represented as y equals x minus 3. And now we can show that with a graph. To graph y equals x plus 3, we start with our y-intercept of 3. Our slope is 1, so we're going to go up 1 to the right 1, up 1 to the right 1. And we'll connect those points because this is a continuous function. So there in red is your y equals x plus 3, your original linear function. Now let's graph the inverse. Let's start with our y-intercept of negative 3. It has the same slope, so up 1 over 1, up 1 over 1, and connect because it's continuous. And please notice that these inverse functions are mirror images over the line y equals x. So let's get practice with one more equation. The linear function is y equals 2x plus 6. Once again, we'll replace y with x and x with y. Let's rewrite that equation so that the y is on the left-hand side. Don't have to do this, it's just what a lot of people feel more comfortable with. We do want to get y by itself, so using inverse operations, we'll subtract 6 from both sides. Now to get y by itself, we want to divide everything by 2. And finally, we want to rewrite the equation so y is all by itself. And instead of x over 2, we'll say 1/2 x. So y equals 1/2 x minus 3 is the inverse of the original function, which was in red. So what we're going to do is we'll do the same thing just to prove that these are inverse functions. We'll graph them on the same coordinate plane. We'll start with our given linear function. The y-intercept is 6. The slope is 2, up 2 to the right 1. Now from your y-intercept, let's go down 2 and to the left 1. And let's connect those points. So there in red is your function, y equals 2x plus 6. Now we want to graph the inverse of that function. Let's start with negative 3 on the y-axis. That's your y-intercept. And the slope is 1/2. So these lines will not be parallel. So we're going to go up 1 and to the right 2, up 1 to the right 2. Let's connect those points. And always a good idea to draw your reflection line y equals x just to justify that in fact these linear functions, which are inverses, they are also mirror images over that line y equals x. So let's summarize what we talked about today with function inverses. First, an inverse of a relation is represented in a table by switching the input and output. If both the relation and the inverse are functions, then the two relations are called inverse functions. An inverse of a relation is represented in a graph. It's found by reflecting the graph across the line y equals x. So that's how we find the inverse of a relation graphically. The inverse of a function represented in an equation is found by replacing the x with y and y with x in the original equation and solving the new equation for y. That's how we find the inverse algebraically.